Let's take a seat and we can get started with our compiler workshop. So just a little bit of introduction. I believe this is the first time we've ever had a compiler workshop, so it's very exciting. One of the lines I've been using actually is this. If you want to work on networking tomorrow, work on compilers today. Been saying that probably about 2 years, and now I think we're getting to the point where it's becoming more and more evident. Compilers are integral to networking in the future. We know this from eBPF, but I think it's expanding way beyond that. I also believe that a lot of the opportunities in networking, especially in performance, are going to come through what we can do with compilers. It's just at that level. And then obviously with the AI and machine learning hooks, that'll also only make that even more true. So we have a good lineup today. So we're actually going to start with, I believe, a video from Neil on nanotubes, so turning XDP code into custom hardware pipelines. And Valan Chandar from Intel will talk about eBPF to transform into FPGA. And Felipe will give more of a general compiler future of networking.
Yeah, I believe the eBPF transform to architecture is Neil. And Balachandra talks about P4 to eBPF and other things.
Okay. Sorry about that. Okay, with that, I believe we have the video presentation.
Hello, I'm Neil Turton, and today I'm going to tell you about the nanotube compiler, which I've been working on at AMD. Our aim with nanotube is to offload XDP programs to an FPGA SmartNIC to give performance back to the application. Of course, one benefit of offloading is reduced host CPU utilization, but I think a more important one is a reduction in the memory and cache bandwidth used. Whenever data is transferred from the network device to the host, it gets stored in either DRAM or a cache. Storing the data uses bandwidth, which could otherwise be used by the CPU cores. This will slow down the cores if latency-sensitive transactions get delayed, or if the cores are limited by the bandwidth to DRAM or the cache. If we can drop a received packet on the network device or send it directly to one of the network ports attached to the same device, then it doesn't need to touch host memory at all. This will happen in a packet filtering or port redirection use case. If the packet does need to be sent to the host, we can at least send it to the correct receive queue. This happens in an RxQ redirection use case. We offload eBPF rather than something else for compatibility. It's easy to program, and there are existing programs which use it. To get high performance, we convert the XDP programs to FPGA logic. For those of you who are unfamiliar with them, FPGAs are devices which are programmed using a hardware description language, rather than a sequence of instructions to be executed on a processor. This is the same kind of language which is used to design integrated circuits, so you can think of FPGAs as reconfigurable integrated circuits. On an FPGA SmartNIC, we have reconfigurable partitions which can hold XDP programs or other user logic. Since FPGAs are so different from CPUs, the program needs to be transformed extensively to produce a high-performance design. We convert the program to a pipeline which accepts a stream of packets on one side and produces a stream of packets on the other. The part of the pipeline nearest the input processes the packets first, so it corresponds with the first part of the program. Similarly, the part nearest the output corresponds with the last part of the program. Packets flow through the pipeline and get processed as they go. All the local state associated with a packet flows through the pipeline with it, so the packet data is always near to the local state, making it easy to access parts of the packet. The pipeline includes logic from the application, logic to access packet data, and logic to access maps. The logic to access packets and maps comes from the nanotube library, which is included with the compiler. The pipeline is specialized to suit the application. The number of stages and the contents of them will vary depending on the structure of the program. A pipeline works well for the packet processing logic because there's no need to combine information from more than one packet, but we need to take a different approach for eBPF maps since they contain long-term values which can be written when processing one packet and read back when processing a different one. We also need to be able to access them from different parts of the pipeline because a program can access the same map more than once for a single packet. To make this work, we keep each map as a separate unit away from the pipeline. To access the map, the pipeline sends a request to it, and the map sends a response back. The diagram shows a simple example. As a packet enters at the left, the program reads some bytes from it. These bytes are then processed by some user code. The code can send a request to map A if it wants. The packet and associated program state are stored in a FIFO and transferred to stage 2. The packet and state are then associated with a response from map A, if there is one, and processed by some more user code in stage 2. It can send a request to map A, or map B, or neither, or both. Again, the packet and associated state are stored in a FIFO and transferred to stage 3. Stage 3 collects the packet, program state, and any map responses, and some user code processes them. Finally, some bytes are written into the packet, and the packet is sent on its way. It would be difficult to design a pipeline like this by hand, so Nanotube automates the transformations so that you only need to write XDP code. To compile an XDP program written in C, the user would normally run Clang with an option to generate eBPF bytecode rather than native machine code. This produces an ELF file which can be loaded into the Linux kernel using the IP command or BPF tool. This process can be broken up into two steps. The first one uses Clang to generate LLVM intermediate representation, and the second uses the LLVM tool LLC to generate eBPF bytecode from the LLVM IR. We extend this flow by running the Nanotube compiler on the LLVM IR. It performs the transformations on the code to turn it into a pipeline like the one we've just seen. The result is written out as C++ in a form which can be compiled with the existing Vitis HLS tool. HLS stands for High Level Synthesis. The generated C++ is in a similar language to the original source code, but it is structured to match the FPGA logic rather than the original software. Vitis HLS then generates low-level Verilog, which describes the operations to be performed on each clock cycle. The Verilog is compiled using a tool called Vivado to produce an FPGA bit file, which can then be loaded onto the FPGA. In parallel with this, we will take a hash of the ELF file to be used as an identifier by the net driver. When the net driver is given an eBPF program by the kernel, it will compute the same hash, allowing it to locate the bit file in the FPGA or on disk. FPGAs are good at processing data in parallel, but they have limits. It wouldn't be efficient to pass a 1500 byte packet between two pieces of logic on every clock cycle. Fortunately, we don't need to. When the packet sizes are large, the packet rate will be low because the network bandwidth is limited. That means we can represent each packet as a sequence of packet words which flow through the pipeline. Each stage of the pipeline is expected to process one packet word on each clock cycle. The program state travels through the pipeline with one of the packet words. Here's a simple example of two stages which could be partway along a larger pipeline. On the first cycle, the first word of a packet enters stage N. The stage might take multiple cycles to process a word, but it can still accept another word on the next clock cycle. The first word advances to make room. If the program needs to access a later part of the packet, then the state needs to be delayed until the required word arrives. Once the word has arrived, the state can move on. If the program now needs to access an early part of the packet, then the state and packet words are written into FIFOs. The next stage can then pop the state and the required packet word at the same time, allowing data to be transferred between them. I've only shown one packet here, but the next packet could follow immediately after the first. There are several advantages to our approach. First, we can process many packets in parallel, accepting and producing one packet word per cycle in the best case. The fact that there's dedicated hardware to handle the packets means the performance will be deterministic. The bottleneck will be the bandwidth of the packet bus or the access rate of one of the maps. An important point is that we adapt the compute resources to suit the program. A pipeline stage can use a small part of the FPGA or a lot of it depending on its needs. We also don't use any chip space for instruction fetch logic, instruction caches, branch prediction logic or load balancers. The packets simply enter the pipeline and get processed by it. On the downside, we don't have instruction caches or branches. We have a spatial architecture, which means that all the program must be resident somewhere on the FPGA. If there's a code path which is rarely used, then it still needs to be there, taking up space. We can't spill the code to DRAM and fetch it when it's needed. That said, in the programs we've looked at, the rarely used code paths tend to be quite short, so they won't occupy much space. Another disadvantage is that compilation takes a long time to complete, often hours. That's because FPGAs are difficult targets to compile to, so the algorithms used take a long time. That means it's not feasible to compile the eBPF program when the user attempts to load it. It will need to be compiled ahead of time and then loaded when it's needed. Finally, our approach uses vendor-specific tools. We see why that's not desirable, but we needed to use those tools to produce FPGA bit files. Potentially, the nanotube compiler could be adapted to work with other vendors' tools by modifying the way the HLS code is generated. We don't know enough about those tools to say how difficult it would be. Nanotube works by performing a series of passes on the code, and this is the current list. The first pass converts calls to eBPF helper functions into calls to what we call the Nanotube API. We use this API internally as we transform the program. You can see there's a long list of transformations we apply. The final pass writes each function as C++ code to be generated by Vitis HLS. I'll go into some of the passes in more detail. Here's an example of a transformation performed by the eBPF to NT pass. The pass operates on LLVM-IR, but I've converted that to C to make it more readable. The conversion to the Nanotube API is fairly direct. You can see here that accesses to the XDP context have been converted into function calls. The mem2rec pass finds pointer accesses in the program and converts them to read and write requests. This example is a program which reads 2 bytes from the ether type field. Before the pass is run, the read is performed through a pointer to packet data. After the pass, it's done using a function call. They have the same effect, but they're done in different ways. This step makes it clear that the access is to the packet and not any other region which could be accessed through a pointer. It moves away from a model with a single address space to a model where each memory region has its own access mechanism. That means we don't need to generate logic to access a map entry when the program is accessing the packet, and vice versa. Packet or map access function calls will be converted into pieces of logic to perform the access in an efficient way. The restrictions imposed by the BPF verifier make it possible to analyze the program and make this kind of transformation. The converge pass makes all the Nanotube API calls unconditional. In the case where a call should do nothing, the parameters are modified to indicate that nothing should be done. This step is important because each call will be turned into a section of pipeline which will do something for each packet. It might check its parameters and decide to pass the packet on unchanged, but that's not doing nothing. On the left is an example control flow graph. The program starts executing at A and decides whether to continue at X or B. If it goes to X, then it accesses map A and then continues at C, and so on. There are 3 paths through this program: AXCD, ABYD, and ABCD. One of the paths accesses the map at X, another one at Y, and the third doesn't access the map at all. Notice that none of the paths access the map more than once. The only path through X continues to C and D without passing through Y. Places where the program accesses the packet or a map have a cost, so the converge pass merges compatible accesses. You can see the result on the right. The map accesses at X and Y have been merged into a single XY access, which is unconditional, but the behavior will be the same. Any map access we want to perform happens at the XY node. In the case where we don't need to perform a map access, we still pass through the XY node, but perform a no-op when we get there. Following this, the pipeline pass breaks up the program into separate pipeline stages. It decides where to break the pipeline and splits each stage into a separate function. Stages need to be split for accesses to maps and for some packet accesses. Each pipeline stage is represented as a separate function, so instead of having a single large function, we have several smaller ones. The FIFOs between adjacent stages and between stages and maps are inserted at this point. That's an overview of what the compiler does. Let's turn to the changes we'll make to the net driver. We plan to load the XDP program onto the SmartNIC using the existing BPF system call and offload callbacks into the net driver. As things stand in Linux at the moment, the user space program is expected to perform 3 steps when an XDP program is being offloaded. First, it creates the maps. Next, it loads the program itself and uses file descriptors to associate the program with the maps it uses. Finally, it attaches the program to the XDP hardware offload hook. At this point, the program starts to process incoming packets. Each of these actions from user space has one or more callbacks into the net driver. There are also callbacks which are used when accessing map entries via the BPF system call. The sequence of events when loading a program is inconvenient to us, as you'll see, but I think this difficulty is best handled in the net driver. It looks like we won't need to modify any of the kernel interfaces. Let's follow through to see how these steps will work when loading a program onto the FPGA. We start with a clean slate, where no bit file has been loaded. Then, user space makes system calls to create some maps. These maps are marked to be offloaded, and they will be later, but at this point we don't know where to put them on the SmartNIC. We haven't loaded a bit file into the partition because we don't know which bit file to load. That's because we haven't been told which program will be used. Since the bit file contains the implementation of the maps, we can't offload them yet, so they will need to stay on the host. At this point, user space could make system calls to modify or query the maps. I've not seen code in the loaders to do that, but there's nothing to stop them from doing it. It could be useful to populate the maps before attaching the XDP program, so that the maps have the correct contents when the program handles the first packet. That means we need a basic implementation of the map operations in the net driver. That's awkward, but at least it can be a simple implementation. Next, user space makes a system call to load the XDP program. At this point, we could load the bit file, or we could wait until the program is attached. I'll show what happens if we wait. When the XDP program is attached to the offload hook, we load the bit file. We plan to invoke a user mode helper to do that part. As I mentioned before, this bit file will implement the maps which are used by the program. We can identify these maps by examining the program which is being attached. We will migrate these maps to the SmartNIC and then mark them as being offloaded. Finally, we will flip a switch on the SmartNIC to send packets through the newly loaded pipeline. Next, I want to talk about how the offloaded maps are accessed by the net driver when a BPF system call is made. We could add a separate control interface to each map and perform the accesses through that. We decided not to do that because it involves adding a separate control port and a lot of extra wiring to connect it to all the maps. Instead, we decided to handle these requests in the same way that we handle network packets. When a network packet arrives, it's handled by the pipeline and can send a request to the map and receive a response. We'll do the same thing when accessing the map from the net driver. The net driver sends a control packet to the pipeline containing a request to be sent to the map. A control packet is just like a network packet, but it's marked to indicate that it should be handled specially. The pipeline sends the request to the map, receives the response, and puts it into the packet. The control packet containing the response is then sent back to the host to be processed by the net driver. To make this all work, the compiler injects code into the program to detect control packets and handle them by performing map operations. The compiler is actively being developed, and it's working as a proof of concept. We've shown that we can perform the required structural transformations, and we've tested it with the Catran load balancer from Meta. That largely worked, but we identified a bug to do with the way maps are accessed, which we're in the process of fixing. We also needed to make some small modifications to the Catran source code to avoid using per CPU maps. It doesn't make sense to offload those because they are tied to the number of host CPU cores, which isn't related to the network device. We expect to achieve line rate on 100 gigabit Ethernet, although we haven't run control tests yet. We've had programs running on 2 different Alveo SmartNICs, but we've still got work to do. Our map support is very basic, and we're working to improve it. We've also not started making the changes to the NetDriver. You can download our code from our GitHub repository. It's open source under the MIT license. If you've got questions or want to get in touch, then please email us. Also, Ed Cree, who works on our NetDriver, is at the conference in person, so feel free to talk to him about what we're doing. Here's a message from our lawyers. Thank you for listening.
Are there any questions about the presentation?
Back there.
Who is the person that is in the conference so I can talk to? Okay, there you go. I just blind.
I have a question. So Neil, you said, I guess this is still prototype level, but do you know what the update rates are on that control path? You showed a control packet going from the driver. While you're answering that, maybe I'll have another question. So I was kind of surprised you said there was only 10 entries per map, or could you do millions, hundreds? What happens if you start overflowing?
Yes, so the 10 entry limit is just because we're prototyping. We're working on a better implementation. There was the first question was about the update rate of the control path. So we've not done any testing of that.
Is it milliseconds?
Potentially it could be quite high. Okay, it seems like we've fixed the audio problems now.
Yeah, we can hear you.
So yes, the update rate from the NetDriver, it's at the moment it's going to be limited by the infrastructure because it's going to involve a BPF system call, which then sends a packet to the NIC and then receives a packet back from it. Potentially we could improve the speed of that by sending packets, multiple requests in sequence, and the response, and collect the responses when they come back. But I don't think we can do that with the current infrastructure, the way that the hooks work at the moment. We'll have to handle them one at a time.
Okay, maybe we'll take it offline.
I do have a question. So we know the verifier is necessary when building kernel code. I'm wondering, are there any additional constraints that have to be considered when compiling the eBPF code into firmware?
So in principle, it should need fewer checks rather than more. The offloaded program doesn't have access to kernel memory, so it's not going to be trampling on stacks or anything like that. So I can't think of any extra checks that are required. So the interface to the kernel, to the offloaded XDP program is simply packets come in, packets go out. So there's no DMA interface there. That's so yeah, we don't need as many checks.
Okay, so I guess it's interesting, so we'll have to see how this scales. So I would have a lot of questions about when things get complicated, programs get larger, how do we keep synchronization between what the kernel is running and what's being offloaded, since they're compiled in different paths. So, but it is interesting work to me. Thank you.
Thank you.
A couple questions back there.
So in the HLS2 synthesis steps, have you had to think about how to handle timing closures on the FPGA and how to handle like timing failures?
So far, we've had a lot of success with timing closure. There may be cases where where we fail to close timing, but generally the Victus HLS tool does a good job of splitting logic between clock stages so that we can actually meet timing.
I just wanted to say that there is BPF standardization effort going with IETF right now. And because you guys integrating BPF into hardware, you might be interested in the effort.
Yes, that's certainly something that we're interested in. Thank you for that.
Okay. No more questions. Thank you.
Okay, so myself, Balachandar, and I have my colleague Komal Jain also joined along with me. So at Intel, we have developed the P4TC compiler backend and added this into the p4.org, which is hosting the P4 open source compiler framework. And our first upstreaming into p4.org was done in the month of May 2023. And so in next 20 minutes or so, we will run through about a brief intro on the P4 language as such, and then we'll briefly touch base on the compiler framework, and then how did we add the P4TC backend, and we will also briefly talk on the P4TC compiler output file and how does it loaded onto the P4TC execution environment so that you can experience the P4 programmability on the TC target itself. So I'm handing over to Komal Jain to walk through the presentation. Komal, over to you.
Thank you, Bala. Can you hear me?
Yes.
Yeah. Okay.
Yeah, we can hear you.
So I'll talk about the P4 compiler backend for P4TC.
Okay.
Yeah. So P4 is a high-level domain-specific language for programming the data plane of the network devices. P4 language on a high level can be viewed as four sub-languages for code language for expressions, type, variables, statements. Then a sub-language for describing parsers, a sub-language for describing the match actions and the control blocks, the control flow, and a sub-language for describing the architecture file. Next, Mala. So this is the high-level open source compiler framework. As you can see, a P4 program consists of two parts, a user program and one is the architecture file. So the architecture file is also a P4 file. It normally has structures and pipelines that are present in a particular target for which compiler is written. The architecture file serves as a contract between the program and the target, and the P4 program uses this architecture file as the base file and defines what has to be done in each of the packet processing pipeline blocks that are given in the architecture. If the architecture has a parser and a control block, the declaration will be present in the architecture file, and what has to be done in the parser, what type of parse graph has to be implemented, will be there in the user program. So this so you can see on the high level there are three parts: the front end, the mid end, and the back end. The front end is open source, and the mid end and the back end are customized, and which takes the underlying architecture specific policies. For example, if you're developing a compiler for P4TC, then for P4TC architecture specific policies, and yeah, and then the compiler generates the output file. uh, it can be assembly file, it can be whatever file you want to generate. Next slide. So anyone can extend support for their device by developing their own compiler by using the front end and mid end from the open source and enable their own backend. So like you can see in the picture, uh, the front end is open source. Here IR represent the intermediate representation while going through one pass to the another pass, and you can add your own mid-end and back-end and generate the specific code for your target. Next slide. So here you can see the fixed components are the blue blocks, which is your front end, and the mid end, there is a library of pre-built passes in the open source, which, and you can also add custom passes according to the architecture requirements, and the mix and match of this uh, comprises your mid end, and then you have the back end and the code generation, which results in the output file. Next slide, Bala. So this is uh, a mapping of the data plane to the P4. So we get the packet metadata and the packet header as the input to the packet processing pipeline. And the first block is the parser. The the parser parses the parse graph, which the user has defined in the P4 program, and then it passes this packet to the next control blocks. So the control blocks are nothing but a match action units. There is a table lookup performed for the specific keys you mentioned in the table, and accordingly the corresponding actions are executed. Then the packet is forwarded to dparser, uh, which updates the header and the metadata, and uh, there can also be a recirculation if required, and this is how the packet gets out of the processing pipeline. Next slide. So I'll talk about the P4TC environment. We have two programs coming as input to the compiler, the P4 program and the architecture file. Like I said, the front end and mid end are open source, and we have extended the backend. The TC backend generates 5 files: the template file, the introspection JSON file, and the eBPF base C files. There are 3 files. The one is for parser C file, the control block C file, and then the header file. These files are loaded into the kernel using the netlink, and then the runtime programming can be done. Next slide. So what are these files? The template file, this file is a shell script that forms the template definition for the various P4 objects like table, actions. The JSON file, this is an introspection file which is used by the control plane for the runtime programming. And then comes the C and the header files. So the backend for TC, we reuse the code from the P4C eBPF library for generating the C files. P4C eBPF is an existing open source backend compiler, and the three files are the parser C file that represents the parser definition, the control block C files, which defines the rest of the software data path, the header file, which defines all the structure definitions and the include files. Next. So here I have taken a small code to explain how does the template file look like, and how does the C file look like. So on the left hand side, you'll see there's a control block definition. It so I have defined a single table which has a single key and one action, send underscore nh. Sorry. So and then the table is applied in the apply block. So for this, we in the template file initially will create the pipeline with the unique pipe ID number, and it will have the number of tables we have in the specific in that program. Then we create the definitions for actions and the tables. So action also has a unique action ID number followed by the incoming parameters. Uh, so you can see we have port ID, MAC address, and sorry, DMAC and the SMAC coming in, and each the type of the uh, of the incoming parameters as well. And then we just activate the action. Then we define the table. In the table, you can each table has a unit table ID number with the key size. So here we only have one key, which is 32 bits. So then the table entries, how many entries are there in the table, and the corresponding actions which are attached to that table, and we make the pipeline as ready. So this is how the template file is generated. Next. So eBPF base C code. So on the left side, I have taken an example of a parser. It's a very small parse graph I try to show over here. So you can see we have two states, the start state and the parse Ethernet state. The compiler will optimize it to one state only because we are just navigating from the start to parse Ethernet. So in the start, you can see we are extracting the header Ethernet initially, and then uh, what is according to what is the value of the ether type, we will either navigate to accept or reject state. So on the right side in the code, you can see initially we just see if the size of the header Ethernet uh, l- is less than the entire packet size. If not, we just the packet is just too short and we can't retrieve the data. So we just drop the packet and go to reject state. Uh, or else we will extract all the fields of the extract, and then retrieve the value of the ether type. If it is 800 like I mentioned, go to with this, I guess some typo, go to accept or else go to reject. And in the reject state, we will just terminate the pipeline and return next. Uh, then I have taken one example of the same example previously which I showed for the template file. So we have the same table, one key and one action. So for this in the eBPF code, initially there'll be the data structures created for this. Over here, we have table key and the table value. Key will be the number of keys you have. So if you can see the structure, the first parameter is the key size, and because we have only one key over here, so you can just see field 0 or else you can see field 1, field 2, so on. And then for the corresponding key, we have the value. The value will have the action structure, and we also map this to the template. So you can see the P4TC entry act structure where we are giving the pipe ID number and the table ID number. This is how it will be mapped to the your template file. And then we just populate the data. The key size is 32. What is, the field name is source address. Next slide, Bala. And so using the k funcs, we do a table lookup, and if there is a hit, we get a value, or else not. If there is a hit, then we execute the action statements, or else we'll just terminate the pipeline and return from there. Next. So I have attached a small clip over here. This will show. We have just cloned the P4C repo and compiled it, and how the output files look like. So I already have cloned and did a build over here. So, P4C, PNA, P4TC is the executable file of the compiler for the P4TC, which takes the input file, the file which we want to process, and followed by the output paths where we want all the output files to be generated. So if I just go in that output folder, you can see all the 5 files which I talked about: the template, the JSON file, the parser C files, and the H files. So it's the same example which I showed in the above program. So, and I won't open all the files. We can. This is there in the open source, so you can refer. And there are sample programs also there to try. This JSON files is for the runtime programming for the control plane. Yeah. This has the header files has all the structure definitions and the include files, the architecture include files. That's all I had on this slide. Next, Bala. So coming on the future work, we are working on implementation of P4 actions. So P4 program can also interact with objects and functions provided by the architecture. And there are 2 types of supported actions: architecture specific actions, which are PNA, PSA. We plan to support PNA only as of now, and the custom actions, where user can define their own action definitions in the program and use it accordingly. Next, we also want to reach at a stage where a same P4 program, we would be able to compile with both the P4TC compiler and any vendor specific compiler. And we also plan to integrate the P4 test gen for P4TC. So P4 test gen is a tool which automatically generates the input output packet tests for P4 programs. Next. These are some reference links. Thank you. Any questions?
Okay, as was introduced in the beginning, so compilers are the future of networking, right? So one of the points that compilers are going to be the future is because compilers are kind of wizards in a way, because packet classification and handling is not simple anymore. It's quite complex, and you have a bandwidth of hundreds of gigabits, and possibly we're going to see even more in the near future. And optimizations have become too complex for handwritten code. And compilers, they can feel magical on the optimization sometimes. They do optimizations that are not obvious as looking at the problem directly. And imperative C code is not appropriate for packet classification abstractions and concepts. And that's why we see several languages being created, as P4, for example. Even SciPanda has its own declarative framework for C language, so it's not an imperative C code. It's actually a framework to actually define parsers in C code, but in a declarative way. And then I'll show how that makes a difference, a huge difference for compilers. We also have what we call parser intermediate language, which is a JSON declarative format for actually representation of parsers. We're working as well on parser MLIR, which is the multi-level intermediate representation from LLVM, creating a new MLIR language for parsers specifically too. And we can see that LLVM-IR is also very interesting intermediate representation that we use for optimizations and also for pattern matching, where we can actually extract information and semantics from C code, declarative or not declarative, in a way that we can actually transform that information to do optimizations. So compilers are that, right? So they are transformations of language to languages, okay? So on SciPanda, we have this, we do have a backend for P4, which does, it's a proof of concept backend, but it does transform the P4 parser itself to parser intermediate language, which is a JSON definition of parser. We also do read actual C code using the declarative SciPanda framework library, but the actual parser definition on that. And we also transform that through a front end to a parser intermediate language. Then we have the backend on this representation here, which transforms this parser intermediate language to SciPanda hardware instructions, which are highly accelerated. And we also have a backend that transforms parser intermediate language to P4 as well, which can be used for several devices that actually have accelerations for P4 with P4 compilers. We also have TC classifier backend too, which transforms to the P4 TC project. And we also transform to eBPF programs as well. And this parser intermediate language and our framework for backends, front-end backend, it's easily extendable to other kinds of end results that we want for different kinds of workloads and hardware accelerations. So this is one of the pattern matchings, for example, that we do on the front-end SciPanda compiler, which transforms C code and LLVM intermediate representations to actual declarative information. So we see there in LLVM intermediate representation the IPv4 length function, which is going to read how many bytes are there in this IP packet, which is actually, you can see that the value is actually multiplied by 4, and it has a mask because it's just a single nibble, and the length of reading is 1 byte masked by a nibble. And that is extracted by pattern matching in C++. We also use the AST of Clang to actually get information, debug information for actually knowing where metadata is extracted with naming of C. But in this case, for actual expression semantics that we are actually extracting, we extract directly from LLVM intermediate representation, because it actually gets a lot of the C AST high-level definitions. They are actually already lowered to a simple load store and arithmetics. So we do pattern matching as these expressions are threaded together. We also have some branching that is possible. So, for example, for error checking, things like that, we also do, which is usually the final LLVM instruction. And we do transform that to that JSON. That JSON there is actually the parser intermediate representation. A part of that we actually represents the IPv4 node with the header length. We are going to see later how it actually gets to the next proto by getting that information, for example, from P4, from another front end, right? So this is the backend to our P4 backend, proof of concept, that transforms P4 to parser intermediate language. We can see that it's a definition of a state passed before IPv4 inside the parser function. It extracts the whole data for IPv4. That's how a lot of definitions of P4 does, because they actually reconstruct the packet. So the backend actually has this offset matchings from the headers, because it actually uses the selection on the data that was already extracted. So we actually follow through with these offsets and calculate the offsets of the packets from there. So the transition goes to another pass state, right? And the pass states are very well translated to the concept of pass nodes in the parser intermediate representation. So you can see that we're able to actually extract the parser IPv4 as a pass node there, which has the same name. We know how many bytes they are going to have at minimum, because that's how many is extracted in the data. The next proto is actually what the select expression is actually doing, so it actually knows how it's reading from the packets itself and how it's actually using. In here, it's not showing the table, but the table is going to be the proto TCP goes to the pass TCP node, and the proto DP constant actually goes to pass DP pass node. We have the definition of the metadata extraction, which is just what will be the packets dot extract in P4 language concept, which is the data that is actually extracted for handling later, right? So we can see that we can transform P4 and C from an actual kind of imperative and declarative abstraction to an actual declarative JSON definition that can be highly, much easier, highly optimized for several different kind of hardwares. And that's how Saipem, the compiler backend, does it. He uses the JSON parser intermediate language. We also leverage on the parser MLIR that we're working on, and LLVM intermediate representation, which we generate on LLVM intermediate representation with a specific backend on LLVM, which also has parser hardware instructions accelerators that we actually leverage that for very, very high acceleration of those passings. So it generates hardware accelerated instructions. It can generate eBPF and even P4 again from there. One thing is that we can also leverage on LLVM optimization passes, so it can actually optimize that code. It can actually optimize several kind of optimizations that is done directly in LLVM. And it can be easily extended for other hardware accelerated devices, because it actually comes from a declarative definition of the parser through the parser intermediate language. And yeah, so is there any questions?
And before that, I had one comment. So in the same way that the backend can be arbitrary, so we can support multiple software backend targets and hardware backend targets, the front end also becomes kind of arbitrary with a nice, when you have a good intermediate representation. So right now it would be C, P4, but Python, Rust, pretty much any language that's reasonably descriptive, have something like data structures. Potentially, you could actually implement the front-end language in any language you want, and the back-end targets, all going through the same intermediate representation. So it really is the value of having a good IR.
Okay. So can you explain a bit of the motivation of using JSON as an intermediate language? You need it to be readable or something?
Yeah, we try to be as readable as possible in JSON, although JSON is not necessarily the most readable language, but it's very, very toolable. And we thought that was very, very important as well.
But it's easier to use it on your backend part to parse?
Yeah, it's easier.
Not only for humans.
Yeah, exactly. It's much, much easier because of tooling, right? So we have several libraries in several languages. So it's much easier for that. We also leverage on arrays and objects inside objects for representation. We try to make it as human readable as possible. And actually, Tom has a very, very important role on definition of the JSON parser intermediate language. Because that's the idea, is to even be able to actually write your own parser as a human, right? So it's not just intermediate by being intermediate. It's like a LLVM intermediate representation. You can read, right, and you can understand. That's important because it's important for debugability, because you want to understand what's happening when you have a problem.
Right, thank you.
Hi, I have another question. The back here. Hi. On one of the slides where you're turning, I think, a P4 program into your JSON. Yeah, that one. So on the left, is it correct that it's saying, well, if it's IPv4 and if it's TCP, then run this function. If it's UDP, then run this function. I don't see how the right side is equivalent to the left. Could you explain that a little bit?
Yeah, so I'm not showing the table exactly, but next proto definition of the JSON, it shows a table, pass IPv4 table. And that pass IPv4 table is actually going to contain the actual constant, which is proto TCP. Proto TCP on the P4 side is actually a constant, which is the number that is going to be matched to the IPv4 protocol data. Okay. And that actually goes to the pass TCP. And that is exactly the same thing is going to happen on the other side. The table is going to say, if the constant is actually proto TCP, then actually the next pass node is going to be pass TCP. If it's UDP, go to pass UDP. And the default is accept, which means actually just don't drop the packet, but doesn't go anywhere, doesn't have an X proto, for example, right?
Okay, thanks.
Okay.
So unfortunately, I didn't give Felipe my favorite graph. So I did a big parse node or parse graph. That's a slide when I used to present it, people would take out their cell phones and take a picture. So it's this whole suite of protocols. But the cool thing about this JSON is you can take that graph and pretty much put that into this JSON structure. And the other cool thing about JSON is it's native to that, so you can actually go from the JSON back to the graphical view. And conceptually, you could actually have a graphical input to it, so we could actually program a parser using a GUI, which is kind of cool too.
So a lot of this has been talked about for a few years now, especially the P4TC stuff. Has it moved beyond just POCs and development kind of workflows to some real deployments to start getting a sense of how well it works?
Which aspect? The
kind of all of the stuff that was presented here.
So the parser,
what you're working on with the parser, because you've been doing this for multiple years.
So the parser we presented last Netdev, it was actually a lot of that went into the P4TC project. I don't know how much is still there, Jamel, but that I think is pretty much ready for prime time. I would point out that Felipe and his team have done an outstanding job. When he said that the LLVM and compiler seemed like magic, to me it is. I can't make heads or tails out of that code. But it's pretty amazing what they've done. And the optimizations going into this, and because of this IR split, it works out really well. But the short answer is that part is definitely ready. We can clean it up, and it's usable. The hardware aspects that Felipe was talking about, obviously, there's some more development we want to do. And, going back to the P4TC, It would be very interesting to see if we could figure out how to unify some of those technologies also.
So, Carl, can you put up this remote people as well? Yeah. So for P4TC, I don't see any problem with Panda generating the. If you noticed when Bala was presenting, a parser is separate. You can hand code one if you want. I do believe at this point that a lot more sophisticated parser could be generated by Panda. But to answer your earlier question, P4TC is ready. We've been pushing upstream patches, version 8. We just removed the RFC tag. There's some issues, but after the Netnext opens, we're going to push again. But the unification could be, the parser could be generated by Panda basically today.
Yep, I think we want to go beyond that and go to the rest of it, right, Jamil? So if you can express something in P4TC, then by definition you can convert that back to JSON, which means why didn't you just have a JSON to start with as an intermediate representation? There's a lot of opportunities
I think
in that model.
I wouldn't disagree, but our code is stable. The generated code has been generated for a while now. We've been testing it. That's why we're pushing the.
You have deployments.
There's deployments, not exactly with P4TC, but there's some experimental trial POCs, I would say, going on, and people have been testing this. All right, on real hardware, but our push has nothing to do with the hardware yet. So the hardware, we're going to leave it aside. There's two vendors at least discussing now, AMD and Intel. I'm not sure about NVIDIA, but the software one is totally independent of the hardware offload. Right.
So just one comment. So this code, we do intend to complete it in open source. There is a version of it's called Panda that's a little bit old, but I think over the next month or two, hopefully we'll get back to that and push all of this. Except the hardware, that's kind of proprietary, what we're trying to make money on. But all the software aspects, hopefully we can open the source.
Yeah, I think probably, David, you're asking about it. The original approach was to put the parser inside P4TC with kparser. That is now generated as eBPF. There was some pushback, so what Bala's referring to as a control plus the parser, while the P4C compiler, the open source P4C compiler, generates the parser. Tom's thing could generate the parser as well, right? And I think it could generate a more sophisticated parser.
Any more questions?
Way in the back.
So if Tom can generate a more advanced parser, that means we need the new API when Tom's thing is ready, or your thing will work?
No, it will work just fine. So what I mean by most generated, if you have a very complex protocol, not your existing things, because a lot of these vendors do, a lot of the users like cloud vendors may have their own proprietary protocols. But for the standard stuff, I don't see any problems with, say, generating TCP, UDP, or proprietary parser with headers with options built in. He does a much more, because he can generate multiple languages, right?
So Tom will use Jamal's API once he's ready?
It's eBPF code. You just generate a parser and you run it as eBPF code.
But so he also has hardware, right? So presumably he will be...
Yeah, so the hardware we're keeping out of this. Until the vendors are ready, we're not pushing any hardware infrastructure yet.
I'm happy to wait, yeah.
Yeah. I didn't follow that.
You said you're happy to wait.
No. This has nothing to... Our RFCs, or what we've been pushing, has nothing to do with hardware. This will let them fight it out. It works. It's independent, really. The two vendors, I think they're in agreement. I'm not sure about the third one. But there's bi-weekly meetings that happen on that.
Out of curiosity, how many have ever looked at compiler code or worked on it? Anyone? Wow. Well, you didn't raise your hand. I know you did.
Oh, yeah.
Okay, so hopefully that'll be something we can change in the future. Any other questions?
Thank you.
All right, thank you. Good timing.